In this In the next section, we'll be discussing the physiology of epithelial cell layers. In this section, we'll discuss epithelial layers. Epithelial layers are layers of cells that line body cavities. They essentially function to separate the external world from the internal world. These epithelial layers cells have two different faces on them. The apical face, or the apical membrane, is a portion of these cells which interacts with the lumen of the body cavity. The basolateral membranes comprise the rest of the cell, which interacts with the interstitial space. There are several structural features that are specific to epithelial layers that we'll discuss now. Tight junctions represent the deposition of proteins in the extracellular space, which serve some specific functions. One function of the tight junction is to prevent molecules from moving from the luminal space to the interstitial space in the spaces between the cells. That is, they guard the spaces between the cells to prevent paracellular transport. They also serve to prevent molecules that are embedded into the basolateral membranes from intermingling with molecules in the apical membranes and vice versa. Gap junctions are cytoplasmic connections between epithelial cells, and they allow small molecules to travel from one cell to another cell in order to permit intercellular communication. Desmosomes serve as structural support. They are proteins that are connected with the cytoskeleton of the cells adjacent to where these desmosomes are found, and they serve as structural support. The important thing to remember is that epithelial layers have to be able to tolerate very large changes in their size. If you consider the bladder, for example, the bladder can go from holding approximately 1 liter or so of fluid to being emptied out and having a volume of a couple of hundred milliliters. In order to be able to permit such movement and stretching of epithelial layers, one requires there to be structural features that hold these cells together, and this is the role of desmosomes. The role of epithelial layers can be illustrated with this example shown in this slide. This is a layer of epithelial cells taken from the renal collecting duct. Shown in the middle is a row of epithelial cells. On the left of these cells is the apical membrane, and on the right of these cells is the basolateral membrane. The tubular fluid, or the incipient urine, is being formed, shown on the left, and on the right is the interstitial, or the blood space. It's important to recognize that there is a different distribution of proteins across the apical and the basolateral sides. On the basolateral sides of these membranes, you have a very high concentration of the sodium-potassium ATPase, and on the apical sides of these membranes, we have a high concentration of sodium and a high concentration of potassium channels. The result of this differential distribution is as follows. As the sodium-potassium ATPase pumps out sodium from these cells, this will deplete sodium from the intracellular space, which will drive the influx of sodium from the tubular fluid into these cells. The result of this is that sodium will flow in a single direction. That is, it will flow from the incipient urine into these cells, will be picked up by the sodium-potassium ATPase, and then therefore brought back into the body. This is referred to as vectorial transport because the sodium is moving in a single vector or a single direction. Potassium, by contrast, will do the opposite. Potassium is being pumped into these cells from the extracellular fluid, from the interstitial space, because of the sodium-potassium ATPases. The resultant high potassium concentration inside of these cells will cause potassium to go down its concentration gradient and will move into the collecting duct. This will cause there to be vectorial transport in the opposite direction, driving potassium from the interstitial space to the tubular fluid. This whole process is potentiated by aldosterone. Aldosterone is released by the adrenal cortex during states of either hyperkalemia or low blood pressure. This aldosterone will bind to a cytosolic receptor. That receptor aldosterone complex will drive the transcription of the genes that encode all three of the proteins shown here, the sodium potassium ATPase, the sodium and potassium channels. Therefore, aldosterone will potentiate the vectorial transport of both sodium and potassium via these mechanisms. Another example of vectorial transport in an epithelial layer is shown here. Here we have an epithelial layer of cells in the middle, also taken from the kidney, but in this example from the thick ascending limb of Henle. The right sides of these cells are the apical membranes, the left sides of these cells are the basolateral membranes. Here we have a symporter, a sodium-potassium chloride symporter on the apical membranes, a sodium-potassium ATPase in the basolateral membranes, as well as chloride and potassium channels also on the basolateral membranes. In the case of sodium, we also have vectorial transport. We have sodium being pumped out of these cells and into the interstitial space, thereby depleting the intracellular concentration, which will drive the influx of sodium through the symporter on the apical membrane. Potassium will also travel through this symporter, and this is being driven by the favorable concentration gradient of sodium. Once potassium enters the cells, because of the potassium channels on the basolateral membranes, potassium will travel down its concentration gradient back into the interstitial space, therefore following a vectorial transport mechanism going from the incipient tubular fluid back into the interstitial space. One very important clinical correlation of this transporter is that the loop diuretics, one well-known example here is furosemide. These drugs all work by blockade of the sodium potassium chloride symporter. By doing so, it will not allow these four osmotically active particles to re-enter the body, and therefore water will not follow, which would normally follow from these cells. And this is one way of eliminating fluid from the body. Question. Again, it's July 1st. You've just admitted an 80-year-old man with benign prostatic hypertrophy who presents with new renal failure. Joe Gunner in the emergency department forgot to mention to you that his serum potassium is 6.5, and this is high, and his EKG looks like the following. This EKG should have gotten your attention. At this point, you would do which of the following? A, give dextrose plus insulin. B, give an albuterol nebulizer. C, give furosemide or Lasix, assuming the patient still makes urine. D, give bicarbonate. Or E, call a lawyer. The correct answer here will be to consider doing all of the above. The rationale for this is as follows. Dextrose plus insulin will potentiate the activity of the sodium potassium ATPase. This will be illustrated in the subsequent slide. By potentiating the sodium potassium ATPase, one can shift the potassium from the extracellular to the intracellular space, thereby reducing extracellular potassium levels. The dextrose is given to counteract the hypoglycemic effects of insulin. Albuterol nebulizers, by activating beta-2 receptors in the pulmonary tree, will similarly increase the activity of the sodium potassium ATPase, driving potassium back into cells. Lasix or furosemide, as previously mentioned, will cause the excretion of potassium through the kidneys, therefore lowering total body potassium. Bicarbonate will also potentiate the activity of the sodium potassium ATPase, though indirectly, and this will shift potassium from the extracellular to the intracellular space, and this will be illustrated shortly. The next slide illustrates the mechanisms by which insulin and beta-2 agonists, such as albuterol, lower extracellular potassium levels. Insulin, as mentioned before, will drive the activity of the sodium potassium ATPase, shifting the balance of potassium from the extracellular to the intracellular space. Similarly, beta-2 agonists, such as albuterol, will drive the same process, though through a slightly different mechanism. Beta-2 agonists will bind to a beta-2 receptor. These beta receptors are coupled to G proteins, which will drive the production of cyclic AMP. cyclic AMP in many cells will increase the activity of the sodium-potassium ATPase, shifting potassium from the extracellular to the intracellular space, dropping extracellular potassium levels. Bicarbonate has a less direct mechanism by which it drives the sodium-potassium ATPase. Bicarbonate, by dropping extracellular proton levels, will drive the activity of sodium proton exchangers, which exist on many cells in the body. By driving the activity of that pump, sodium levels inside of cells will increase. By increasing sodium levels intracellularly, this will drive the activity of the sodium-potassium ATPase and therefore drive potassium back into the intracellular space, again dropping extracellular potassium levels. That concludes our discussion of epithelial cell layers.